Welcome to Nuclear Magnetic Resonance NMR Spectroscopy, Part 9. In continuation of our previous section, here the group I'll discuss about is alkynes. We know that alkynes have two types of hydrogens, acetylenic hydrogen and alpha hydrogen found on carbon atoms next to the triple bond. Chemical shift of alkylenic proton is 1.7 to 2.7 ppm, and in case of alpha hydrogen, here the chemical shift value is 1.6 to 2.6 parts per million. And coupling behavior for this type of protons, it is 4J coupling, that is long range one, so the value is very low, very small, that is 2 to 3 hertz. One example is 1-pentyne. Here you can see 4 types of protons environment are available. Here is A type, it is triplet for these 2 protons, neighboring protons, and B 3 to 5, so it is a sextet, and this is the C proton here, and D proton, it's a triplet here. In case of alkyl halides generally have one type of hydrogen, that is alpha hydrogen. You can see the chemical shift value for CHI, it is 2 to 4 ppm. In case of CHBr, it is 2.7 to 4.1 ppm. In case of CHCl, it is 3.1 to 4.1 ppm, and in case of CHF, it is 4.2 to 4.8 ppm. It is on synchronizing order as their electronegativity value increases from I to fluorine. One example, spectrum of chlorobutane. 4 types of proton environment is there here. This is the CH3, this is CH2, C, it has 2 plus 2 or 4 plus 1, that is 5 quintet, and the D1, it is a triplet. In case of alcohols have 2 types of hydrogen, hydroxyl proton and the alpha hydrogens, those on the same carbon as the hydroxyl groups. Now chemical shift of OH proton is 0.5 to 5 ppm depending upon other factors, that is hydrogen bonding or something others. In case of CHOH, it is 3.2 to 3.8 ppm, and no coupling usually in case of CHOH with these 2 protons, or sometimes it's a 3J coupling, so the value is nearly 5 hertz. Example is 2-methyl-1-propanol. You can see it has 4 types of proton environment, and these 2 sets of proton have identical environment, they are chemically equivalent, so, and magnetically also, so they all 6 protons gives a doublet here for the presence of this proton. And B proton B, it's a nonate because 3 plus 2, 6, 8 plus 1, it's a nonate. And this D proton, here it is, it's a triplet, and C proton is also a triplet for the presence of CH2. In case of ethers have one type of hydrogen, the alpha hydrogens, and chemical shift value for this proton is 3.2 to 3.8 ppm. Example is butyl methyl ether. You can see here 5 types of proton is there. Proton environment is there. It's for CH3, CH2, another CH2, and it is the another CH2, and this is for CH3. In case of amines, amines have 2 types of hydrogen, those attached to the nitrogen, and that is the hydrogen of amino group, and those attached to the alpha carbon. So chemical shift value for the for those proton attached with nitrogen is 0.5 to 4 ppm, or sometimes it is 2.2 to 2.9. In case of aromatic amine, it is 3.0 to 5 ppm. And coupling behavior, it's 3 bond coupling, and the value is 0. So no coupling here. Example is propylamine. 4 types of carbon environment is here. You can see it's a triplet, sextet, and another triplet. For nitriles, nitriles have a 1 type of hydrogen, the alpha hydrogen, and the chemical shift value is nearly 2.1 to 3 ppm. Example, valeronitrile. 4 types of proton environment is here: triplet, multiplet, and triplet. Now, if there is a lot of splitting, so sometimes it is difficult to identify each one of them. So for that reason, there are some procedure to minimize the coupling pattern, and to isolate or identify each protons. One procedure is like that: spin decoupling. What is spin decoupling? It's a powerful tool for simplifying a spectrum, and is of great value to organic chemists working with complex molecules. It helps in the identification of coupled protons in spectra that are too complex for detailed analysis. This technique involves the irradiation of a proton or a group of equivalent proton with sufficiently intense radio frequency energy to eliminate completely the observed coupling of the neighboring protons. The simplification of the complex spectrum for easy interpretation is done by using an instrument which is with a more powerful homogeneous magnetic field. For example, a 100 megahertz instrument in preference of 60 megahertz instrument, or by some spin decoupling techniques. Another method is isotope exchange. We know that deuterium, the heavy isotope of hydrogen, has been used extensively in proton NMR spectroscopy for 2 reasons. First, it is easily introduced into a molecule. Second, the presence of deuterium in a molecule is not detected in the proton NMR spectrum. Deuterium has a much smaller magnetic dipole moment than hydrogen, and therefore it absorbs a different field strength. In case of ethyl bromide, the deuterium replaces the methyl hydrogens, and the following changes occurs. You can see, by replacing each proton by deuterium, you can see the coupling behavior changes, and finally it comes to a singlet. Shift reagents. Lanthanide series of elements are used as shift reagents. A lanthanide ion can increase its coordination number by interacting with unshared electrons. As a result, the NMR spectrum of the compound that contains a group possessing unshared pair of electron undergoes change and large chemical shift as a difference in peaks is observed. All the shift reagents are mild Lewis acid. Shift reagents separates NMR signals, those normally overlap. Thus, it gives more simplified spectrum. Shift reagents are paramagnetic, so large chemical shift take place. Shift reagents is normally used in nonpolar solvents like CdCl3 or CCl4, etc. And shift reagents provide a useful technique for spreading out proton NMR absorption patterns which normally overlap without increasing the strength of the applied magnetic field. Example, in the proton NMR spectrum of N-hexanol, the high field triplet is distorted, with which represents the absorption of a methyl group adjacent to a CH2 group. The low field broad multiplet is due to the methylene group adjacent to the hydroxyl group. The proton of the remaining methylene group are all buried in the methylene envelope between delta 1.2 to 1.8. So in presence of shift reagent, when the same spectrum is recorded after addition of a soluble europium 3 complex, which is the shift reagent, the spectrum is spread out over a wider range of frequencies, so that it is now simplified almost to the first order. In the spectrum, wedge absorption signal is shifted too far to be. You can see here is the wedge signal, so the other signals, all coupling behavior is a full-fledged clear, so we can identify each peak. So at the end of our journey of NMR spectroscopy, here are some references. Y.R. Sharma, G.R. Chatwal, Jagmohan, B.K. Sharma, I.S. Ravishankar, O.V.K. Reddy, Wheeler Handbook of Spectroscopy, Pavia Lampman, which is very a good book and interesting also for NMR spectroscopy. Scoop D.A., Willard H. These are some reference books. Castor Evie, and finally the Silverstein, and our the more known one, that is Kemp organic spectroscopy, and some material I have taken from Google. Thanks all of them. Thank you all.